Complete the following reaction. So this is an alkyne, specifically propyne in sodium metal. So what you are going to get is CH3, C triple bond C, then Na plus, half mole of hydrogen gas. And then we also have a propyne in the presence of a Grignard reagent, CH3NGBr. So what you are going to get is a CH4, then plus CH3, C triple bond C, then MgBr. So that's the product for this reaction. This is an internal alkyne with silver nitrate. They are trying to do the silver mirror test, but because this is an internal alkyne, there will be no reaction in this case. So here's a no reaction case. And then in the D part, this is a terminal alkyne in silver nitrate. So this one will actually undergo the silver mirror test. And we are going to get CH3, CH2, C triple bond C, then Ag plus nitric acid, HNO3. What are the structures of the following compounds? A, 1,3-dimethyl cyclopentene. So we are talking about a cyclopentene. So let's draw a cyclopentene since that is the parent chain. So this is cyclopentene. Then 1,3-dimethyl. So if this is carbon number 1, then carbon number 2 and carbon number 3. So this is a 1,3-dimethyl cyclopentene. Then the B part is 3Z2S, 2-bromo, 3-methyl, 3-hexene. So we are supposed to draw a hexene. However, we have a 3Z here. So that means that on carbon number 3 and 4, there is supposed to be stereochemistry. Z means 6. So a 6 stereochemistry on carbon number 3 and carbon number 4. So this is how it will look like. So 1, 2, 3, 4, 5, and then 6. So now we are talking about a 3-hexene. So there's supposed to be a double bond on carbon number 3. However, we are also told that there is a bromine on carbon number 2. So there is a bromine here. And then apart from that, there is a 2s. So we are supposed to ensure that the stereochemistry here is a 2s. So let's put the bromine on the dash bond. So this is bromine. And let's put the proton here on a wedge bond. So this is a proton. Now, let's determine the configuration here. Here is 1, and then this is 2, and then this is 3, and the proton is at the back. So it's going in the anti-clockwise direction. So this is a 2s. So let's determine the stereochemistry here. As you can see that there are protons here, and there's also a proton here. So in this case, here is, if we divide this vertically, and here is 1, and here is 2. And in this case too, this place is 1, and this place is 2. So you can see that the 2's are on one side of the double bond, and the 1's are also on another side of the double bond. So this is a Z. So this is 3Z. So you can see that this is the actual drawing of the molecule. So let me redraw it. And the last part of the question says that 4E3 1-methyl propyl 1,4-hexadiene. So the parent chain is a hexadiene. So let's draw a hexadiene. 1, 2, 3, 4, 5, 6. So, and then he says that it is a 1,4. So carbon number 1, 2, 3, 4. So this is a hexadiene. But apart from that, he says that there is a 4E. So that means there is supposed to be a trans on carbon number 4. And you see that this is actually a trans because this proton is pointing this way, and this one too is pointing this way. So this is a trans stereochemistry. Then we have on carbon number 3 1-methyl propyl. Anytime you see a name that has been put in brackets in a name of a organic molecule, know that that is a substituent on a substituent. Remember that this is a propyl. Then we have a methyl on carbon number 1 on the propyl. So this is carbon number 1. So we have a methyl on carbon number 1 on the propyl. We will then take this and join it to carbon number 3 of the parent chain. So this carbon number 1, carbon number 2, and carbon number 3 on the parent chain. So it's going to look like this. So you can see that this is a propyl, 1, 2, 3, and then this is a methyl. So this is 1-methyl propyl, then 1,4-hexadiene, and then we see that there is a 4E on carbon number 4. So this is the structure of that molecule. In this question, he says that explain the following terms. Engine knocking. What is engine knocking? Engine knocking is when fuel burns unevenly in your engine. This leads to pre-ignition and then small explosion in the engine. That is engine knocking. Then pyrolysis. Pyrolysis is the thermal decomposition of an organic compound at high temperatures, usually in the absence of oxygen. Then the second part, he says that we should write a balanced equation for the combustion of cyclohexane. So for example, if you have, let's assume this is a cyclohexane. For combustion process, we need to use oxygen. And anytime you do combustion, the end products are carbon dioxide and then water. So at the end of the day, it becomes, the true equation is C6H12 then plus 9O2, and that will give us 6CO2 plus 6H2O. This is a liquid, this is a gas, this is also a gas. The third part says that name and draw 2 halogenating agents and 2 radical initiators that are used in the halogenation of alkenes. So for the halogenation agent, we have the sulfonyl chloride. So this is the structure of sulfonyl chloride. This is a halogenating agent, and we also have the N-bromosuccinamide. So the N-bromosuccinamide looks like this. This is supposed to be a nitrogen. So this is N-bromosuccinamide. This is also a halogenation agent. Then the radical initiators, we have the dibenzoyl peroxide. So dibenzoyl peroxide looks like this. So this is the structure of dibenzoyl peroxide. And then the last one we can talk about is the N-bromosuccinamide. So the N-bromosuccinamide also looks like this. So this is the structure of the N-bromosuccinamide. In each pair of alkenes below, which is more stable? Here we have 1-methyl cyclohexane and 3-methyl cyclohexane. So let's draw it. This is a cyclohexane, and we have a 1-methyl. And we also have a cyclohexane, and we have a 3-methyl. So this is 3-methyl cyclohexane. So he says that which one is more stable? Now for the alkenes, their stability depends on the substitution around the double bond. The more substitution we have around the double bond, the more stable the alkene is. Now if you look at this alkene, this is a tri-substituted alkene, and this is a di-substituted alkene. since this is a tri, it means that this one, it has more substitution. For example, 1, 2, 3, compared to this one, which is just 1, 2. So it means that this one, which is 1-methyl cyclohexene, is more stable than 3-methyl cyclohexene. Then the B part is 2-methyl 1-butene. So this is a butene, and this is 1-butene, and this is 2-methyl 1-butene, and 3-methyl 1-butene. So this is 1-butene, and this is 3-methyl 1-butene. And he says that which one is also more stable. We use the same thing. So what is the substitution around this double bond? You see that this is a di substituted double bond, and then this one is a mono substituted double bond. So di substituted double bond is more stable than a mono substituted double bond. And then the last one, which is the C part, it says that Z2-pentene. So let's draw Z2-pentene. 1, 2, 3, 4, 5. So this is Z2-pentene. And then we also have here E2-pentene. 1, 2, 3, 4, 5. So this is 2-pentene, and this is E2-pentene. Now, which one of these is more stable? You can see that for this one, across the double bond, the protons point in the opposite direction, compared to this one where the protons point in the same direction. So there is more steric hindrance in this case compared to this case, which has less steric hindrance. The more the steric hindrance there is in an organic molecule, the less stable the organic molecule is. And that will make the E2-pentene a more stable molecule than the Z2-pentene. Provide reactant, reagent, and conditions of product to complete the reaction below. So if you are adding a chlorine gas to this alkene, you are going to get this kind of product. But there will be stereochemistry in solution. And then the next one is this alkene in hydrogen bromide in a peroxide. So this is the Karas effect, or the anti-Markovnikov's reaction. So since it's and for this one we have an alkene together with potassium iodide in phosphoric acid. So this is also an electrophilic radical reaction, but the HI is used to generate. So it's actually a reaction that happens with hydrogen iodide, actually a halogenation reaction. So, but then you need to use HI. But this HI is generated in situ in the reaction together with the phosphoric acid. So at the end of the day, it is also going to obey the Markovnikov's addition, and therefore this will be the product that will be formed. So there is an iodine here, and then there is a proton here.